When you ask a large language model a trivia question and it spits out the perfect answer, it feels like it's just looking it up. But where exactly does an artificial intelligence keep all those billions of facts? We are used to computers functioning like giant filing cabinets. You search for a file, the hard drive spins, and it retrieves a specific document from a specific folder. But an AI does not have a searchable database of facts hidden inside it. Instead of a hard drive full of documents, all of its knowledge exists as pure mathematics. Every historical date, and every recipe, and every piece of trivia is encoded into scattered numerical patterns across a massive neural network. To figure out where those facts actually live, we have to look at the transformer. A transformer is the underlying architecture that powers modern large language models, and it operates using two primary systems. This diagram shows those two main systems side by side. On the left, we have the first piece, called attention. Attention is an operation that strictly handles context, allowing words to pass information back and forth to understand what a sentence means, rather than storing trivia. Since that first system is only passing context around, the hard facts themselves must be buried somewhere inside that second, much denser part of the network. That second system is made up of multi-layer perceptrons, or MLPs. An MLP is a sequence of computational layers that acts as the primary vault where the model's factual knowledge is baked in. Let's trace exactly how a fact gets retrieved from this vault, using a highly specific example. If we feed the network the name Michael Jordan, we want to see exactly how it knows to associate him with his specific sport. This animation shows the very first step. The text of the name is broken down and converted into a high-dimensional vector. A vector is simply a long, ordered list of numbers that the computer uses to represent the meaning of that word. The core job of the MLP block is to take that long list of numbers representing the person and append the mathematical representation of basketball to it before sending it out. This diagram illustrates the mathematical heavy lifting. The input vector flows in and is multiplied against a massive grid of numbers called a weight matrix, which contains the parameters the model learned during its training. Think of this grid as a gauntlet of questions. Each individual row acts as a distinct probe, taking a dot product with our input vector to test how well the data aligns with specific encoded concepts. In our example, the network has tuned one of these rows to act as a highly targeted probe. It's asking, does this list of numbers represent the combined first name Michael and the last name Jordan? If it does, the math yields a high positive number. Retrieving memory in an AI is a process of bombarding a piece of data with tens of thousands of simultaneous equations, all running in parallel, to see which conceptual probes resonate the strongest. But there is a problem with relying purely on multiplication. It's a linear process, which means it's messy. A probe looking for Michael Jordan might accidentally get a partial weak match if it encounters a completely different name, like Michael Phelps. This graph illustrates the solution, a nonlinear function called a ReLU. ReLU stands for Rectified Linear Unit, and it's a simple mathematical logic gate designed to strip away all that noisy, unwanted data. The gate is ruthless. It crushes all negative or weak signals straight to zero, completely ignoring them. Only the perfectly aligned, high-scoring match for Michael Jordan is allowed to pass through the gate and activate a neuron in the network. Once that specific neuron lights up, it acts as the exact trigger needed to retrieve the final fact. It tells the network to grab the mathematical direction for basketball and add it to our original sequence of numbers. If we zoom out and look at the whole model, we hit a mathematical wall. The space where all these vectors live, called the embedding space, has a strict, finite number of dimensions. This graph shows a standard 3D space. The strict rule of geometry dictates that if every distinct concept requires its own completely independent perpendicular direction, like an X, Y, and Z axis, you can only store as many concepts as you have dimensions. A model like GPT-3 has about 12,000 dimensions, yet it clearly knows millions upon millions of facts, far exceeding that hard mathematical limit. To pack the entire internet into a strictly confined space, the network has to be bending the rules of geometry. Researchers believe they've found the mechanism making this possible, and it's an idea known as superposition. Superposition is a mathematical workaround that allows a network to represent far more features than it has dimensions. This graph demonstrates bending that rule. If the AI stops forcing every concept to be perfectly 90 degrees apart and instead accepts directions that are nearly perpendicular, say 89 degrees, it creates enough wiggle room to squeeze an exponentially massive number of vectors into the same space. Because of this dense packing, a single neuron inside the model rarely holds one clean, isolated piece of trivia. Instead, it holds a densely superimposed combination of many different facts simultaneously. By stacking thousands of nearly perpendicular concepts on top of each other, the model multiplies its storage efficiency. When you add a few more dimensions to a space, the amount of data it can hold in superposition explodes exponentially. So, the next time an AI casually recites an obscure fact, remember what's actually happening. There's no hard drive or database spinning up. It is navigating an intricate landscape of matrix probes, decision gates, and overlapping mathematical dimensions. The network has taken the messy, sprawling reality of human knowledge and baked it directly into millions of superimposed fractional weights. If you want to keep exploring the hidden mechanics beneath the surface of modern AI, hit subscribe, and we will decode the next system together.